Hey, what's up, guys? Yeah. So previous video I talked about CH. Oh, so I first talked about CSH game, right? So if you haven't seen my previous video, that you can check it. And then I talk about Bell inequality. Okay, so I talked that if I just told you that if they're Alice and Bob, and if they have like A0, A1, B0, and B1, and such that this AI are belong plus or minus one, and the BR also belongs to plus or minus one, and one can compute this A0 plus A0 B0 plus A0 B1 plus A1 B0 minus A1 B1, and then let's call it S. Right, then easy to see that classical this is S is bounded by 2 and negative 2. And we by proof that if they can share if pair entanglement, if they can share some entanglement pair, 1 over square root 2, 0, 0 plus 1, 1. And if you choose A0 to be Z times direct sum identity, and A1 to be X identity, and B0, B1 will be like 1 over square root of 2, 1 over square root of 2 identity, direct sum Z plus X, and the identity direct sum Z minus X. And if you just directly compute this S, then you can check it's 2 times square root of 2. Okay. So this is the previous two videos. If you haven't seen it, then I will post the link below. Okay. And so today I want to talk about this. So this is the Tsirelson's bound. Okay, so one might ask, so the natural question is that whether S reaches maximum, right? Because we know basically we know that the classical, right, for the classical that it's S bounded by 2, right? For the quantum, we prove that S can be greater than or equal to 2 square root of 2, right? Because I find it quite simple that it's 2 square root of 2, right? So the natural one is that whether 2 square root of 2 is the optimal one. Okay, and this is basically related to the winning probability of this CHSH gain, where cosine square pi divided by a is the best. It's the best. Okay, so basically these Tsirelson sounds give you the answer. So basically, simply speaking, that 2 square root of 2 is the best. By the way, this Tsirelson bound is a very difficult object in a general expression. So this is related to the very recent work called MIP star equals to RE. Right. So if you're interested, you can go online and check this. And I will not talk about this, but this is like also related to this quantum non-local game. Basically, there is a problem called Tsirelson's problem. Deal with general kind of expression, and yeah. So I will talk maybe mention a little bit. Okay, so the proof is very simple, right? So we can start from S, and then start A0 B0 plus A1 B0 plus A0 B1 minus A1 B1. Okay, so you can calculate S squared. A little bit tedious, but this now each only requirement is that this AI or eigen are the operator which has like only plus or minus one eigenvalues. So AI has only plus or minus one eigenvalues. Okay, so simply speaking is that okay, original or is a number, right? But now I allow everyone to be operator, but I still need to force a constraint. So my constraint is that each operator is only plus or minus one eigenvalues. Okay, so and also no, there's also a constraint such that is need one identity. Okay. Basically it's the same as this. I mean, if there are Hermitian, yeah, if there are Hermitian, then they are all both. Yeah, you can prove this. Okay. Right. So if S squared and the computation equals to 4 times identity minus A0 A1 commutator B0 B1 commutator. Okay, so this gives us why, because in the classical that A0 and A1 are commute, right? So if you give me this, then you get S0 S squared is 4i. Okay, so that means that S is less equal to, if you take the expectation value, and then for the content, right? If you content that that we want to find, right? But this guy, if you act as a matrix 2 norm, so matrix 2 norm basically is the largest eigenvalue, or largest singular value, or another way is to say that right. So matrix 2 norm basically is the super of all x equals to 1. X is a vector such as ax, right? So the absolute value of the vector norm. Okay, so this is vector norm, this is the vector norm, and then I take this, and the force the requirement is that S need to be unisphere. Okay, so this is bounded by, bounded by triangular inequality, right? So it's bounded by A0 to norm, A1 to norm. And since this square must be identity, right? So this is bounded by 2. Okay, so this tell you that S square is at most as a 2 norm is bounded by 4 minus, right? Minus needs to be plus. Okay, so S square is bounded by S square 2 norm is bounded by 8. So this gives you S is in general is bounded by 2 square root of 2. Okay, so this proves that 2 square root of 2 is the optimal. Okay. Okay, so yeah, that's it. So let me just mention something about this. Because this guy is interesting. So this is Tsirelson's problem. Okay, and I say that recently, I think it's 2 years previous 2 years, there is a breakthrough called MIP star equals RE. So MIP okay, so let me just quickly say so basically MIP is a complexity class. It's a multi-prover with the entanglement, and the one can show that this is equals to another complexity class called RE. Okay, so this is also related to Tsirelson problem. And so Tsirelson problem can ask the following, right? So you can ask about expression called B, which is U A B X Y P A B X Y, and then you just sum over A B X Y. Okay, so what this guy means that if you have this, right, you can imagine it's a general CHS H game. Okay, so the probability XY is like this is Alice, right? This is Bob. So Alice receive X and output A. Bob receive Y and output B. And the strategy can be probability, right? So it's P A B X Y, and then there's a constant, there's a coefficient that we need to sum about it. Okay. Okay, so we can put this context, right? Suppose that we can imagine that there may be some quantum entangling here. Okay, so we can make this A and B as some measurement of the content, some measurement come from some measurement outcome. So we can, let's say we have AXA right, from HA, let's say HA is Hilbert space to another HA, and BBY is the HB to HB, right? Because as previous CHS game, that this A and B can depend on X and Y, they can do different measurement, right? So given X and A, there will be a measurement. Given a Y and B, there another measurement. Okay. And then let's say we have some quantum states which live in this space. Okay, and so we can define a TT. TT is another expression. It's a soup of, I can consider all the possible phi and all the possible measurement. Okay, I can try to maximize this B, right? So I can have mu A B X Y, phi A X A, and the tensor product B Y. This, right? So I can write these guys this and try to optimize this, right? So this is called TT. Okay, so this is one object. Okay, and then there's another object. So this is called TT, and then there's another object. Okay, so there's another object. By the way, so this guy called tensor product. Tsirelson number. Okay, so this guy is called tensor product. Okay, but one can define another number. Okay, another number is defined as we can have AX right from H to H. H is some Hilbert space, and also BYB to H to H. And but now we require that this guy is 0. Okay. For A, B, X, Y. And then on some special quantum state H. Right. So and now I imagine that those two those two numbers are live in some spatials, live in larger Hilbert space. And I compute this TC, and I take all the soup, then I take all this operator, B, and I still do the sum. Okay, and I can calculate this number. Okay. Okay, so this guy, right? This TC is in general, in general, is larger than, should be greater than TT, right? Because I mean, previously we required that there are live in the spatial, there are live in both there's small HA, right? HB. Okay, so this is, you can imagine this is more like classical one, right? Because I have HA and I have both Hilbert space, and I can do a measurement state which live in the tensor product. Now I can have more larger one. Now this larger one to just require their commute, and but in previous there are live in a different Hilbert space, right? So they must commute. So in general, this TT less equal to TC. Okay. Okay. And so the idea is that for infinite dimensional, these two can be different. Okay. Okay. So the fact which is related to this, might be star equals to RE. Okay, so the amazing breakthrough is this. The amazing breakthrough is like TT is not computable. Okay, so the idea is that since TT that's equal to TC, right? So if TT, yeah, okay. Or simply speaking, TT is not computable. Okay, and right, okay. Yeah, so this is like the amazing results, right? But basically, this tells you that there is no algorithm can compute the winning probability of general non-local game. Okay, and there's much deep thing on this, but I would like to stop here and see you guys next video.